In this series of videos, I describe how to implement a microcontroller core in System Verilog. In today's video, I'll be describing the compare instruction, the load stack pointer instruction, and the add 16 instruction. But first I want to begin with a review. Here's our finite state machine. Every instruction begins in the fetch state, and many instructions just take a single state, so we remain in the fetch state. But some instructions take more than one state, or more than one cycle, and they proceed through the exec2, exec3, and so on. I've already gone over a lot of the code for the core module, but I want to review that and talk about some of the new material that I'm introducing. Remember that we've got these definitions of these type codes for each of the instruction categories, like the register move, the move immediate, and the ALU instructions, and so on. Today I'm going to be talking about the add 16 instruction, the load stack pointer instruction, and the compare instruction. So here are the states of the finite state machine, and here's our definition of the core module. And it contains a number of Verilog registers. We have the state of the finite state machine, we have the program counter, we have this instruction save register, we've got the stack pointer and this MSB register, and then we've got 4 condition code registers. We have a number of signals that are combinationally computed. For example, we've got the instruction. This is the 8-bit opcode of the instruction that's currently being executed. And we also compute combinationally the next state that our finite state machine should go into on the subsequent clock cycle. There are a number of other signals that are computed combinationally, but I'll talk about these in a second when I talk about how they're initialized by default. Previously I talked about this block of code here that controls the clock enable signal. Whenever we press the single step button, we want to raise the clock enable signal for 1 cycle. We've also got the code that instantiates the submodules. We've got the memory module, we've got the instruction decoder module. This takes the current instruction as input and produces the type or category of the instruction that we've got, as well as pulling out a number of different fields from the current instruction. We've got this registers module, which contains the 8-bit registers, and then we've got the ALU module. Here is the code that sets the registers. So on the positive edge of the clock, if the clock enable signal is high, we're going to be updating all of the registers. I'll come back to the reset stuff in a second, but we see that we are always going into the next state. So our finite state machine moves from state to state. And then we have this pattern here where we have a write enable signal, and if it is high, we'll be updating the corresponding register. So if the PC write enable line is high, we'll update the program counter with whatever we've computed it should contain next. Here's that pattern again. If the MSB write enable line is high, we'll update the MSB register. And here's that pattern again. We will update the stack pointer on certain cycles, but mostly we won't be updating it. And then here's that pattern one final time. If the condition code write enable line is high, we'll update the condition codes with whatever's coming out of the ALU. We are also saving the output from the memory unit every time that we are in the fetch state, and we save that in the instruction save register. Now let me talk about this reset material. So the reset button may or may not be pressed, and if it's pressed on the rising edge of the clock, assuming if we're single stepping, we assume we have to press the single step button. But if the reset line is high, then we're going to reset the variables, the registers. The state will be set to the start state. The program counter and the stack pointer will be initialized to 0. And I initialize this instruction save register, although it doesn't get used. I've also added some code here, which you see with this power on counter. So if the power on counter, which is a system Verilog register that I've defined, I'm not showing the definition of it, but it's a few bits that is a counter. And if it is uh, 0 or a small number, then we stay in this reset state where we keep trying to update the registers. The reason I did this is because I was having some difficulties with the FPGA initializing properly. I'm using the ICE 40 chip on the NAND Land Go board, and when I flash the chip and then apply power to it, it doesn't reset properly. And I'm not exactly sure what's going on, and I tried a number of different things to solve this problem, and this is what ended up working. So you can see here that I'm incrementing this little counter, and while the counter is a number that's less than 10, we keep trying to reset these registers. And when it reaches 10, then we reset the registers and move on. Oddly enough, this didn't work when the limit value here was, say, for example, 3. So it does work when it's 10. So again, I'm not exactly sure what's going on. I think probably when it first powers up, it's not in a sort of an inconsistent state, and maybe all the registers are not initialized properly. Again, I'm not sure exactly what's going on. The lattice semiconductor software is, I believe, recognizing the finite state machine and turning it into a one-hot implementation, if you know what that is. And it occurred to me that maybe that's the source of the problem, but I really wasn't able to quite figure it out. But moving on, let's now look at how we set the combinational signals. We set the instruction to be either what's just coming out of the memory, if it's the fetch state, or what came out of the memory previously otherwise. We have signals for the memory unit, and our default signals will supply the program counter and not do an update. We also have default signals for the register unit, and by default we don't want to update any of the registers, so the enable lines are low. And we have default signals for the arithmetic logic unit. We also have a number of signals up here. For example, by default we will always be going into the fetch state next. We'll override this for some instructions, but most will be a single cycle, and so the normal activity is to go back to the fetch state. Our default for the program counter is to increment it, and we're also computing a signal called program counter plus 2, which I won't be using today. For the MSB register, by default we will not be updating it, and for the stack pointer, by default we will not be updating it. However, we do compute some next values. We also compute the stack pointer -1 and -2, which we use for the pop instructions. I'll talk about the add 16 register result here when I talk about the add 16, so I'll save that for later. The body of this construct is a case statement that looks at what state we're in. We're either in the start state, or the fetch state, or the execute state, or execute 2, 3, and so on. And within the state that we're in, we then check to see what kind of instruction we have by looking at the op type value. In the start state, we basically don't do anything. We just allow the memory time to fetch the first instruction. So our defaults for updating the program counter and going into the fetch state are fine. But for the other states, we look at what category of instruction it is. We might have a register move instruction, or an ALU instruction, or a compare, or load stack pointer, and so on. The same is true in the exec state. Again, we look at the type of the instruction and case on the different kinds of instructions that we have. Let's look at what happens when we execute an instruction. So imagine that we're executing a move immediate instruction. The finite state machine begins in the fetch state, and the program counter has already been incremented. So this move immediate instruction must have come out of address 3. On the previous cycle, we fed address 3 into the memory unit, and then we got the move immediate opcode out here. The move immediate instruction is going to require 2 cycles. It's a 2-byte instruction. The opcode is followed by an 8-bit immediate value, so we're going to need a second cycle to read memory again. So what we're going to do when we're in the fetch state is just supply the current program counter, which is the address of the immediate value, to the memory, and on the next cycle we'll get the immediate value out. So if we look at the code, we see that when we're in the fetch state and when the instruction is a move immediate instruction, we're going to go into the exec state. We're not doing anything else differently because we will be incrementing the program counter and reading from memory. So the defaults are just fine. So we go ahead and read from the memory and get the immediate value here, and we increment the program counter. So now we're going to need to load it into one of the registers. So at this point we will be supplying this updated program counter, which is now the address of the next instruction, to the memory, and that's in preparation for fetching the next instruction. We will also be sending signals to the register unit that will cause this value to be loaded into whichever register is selected. So if we look at the code here, let's go down to the execute state, and for the move immediate instruction, we see that we are feeding into the register unit whatever data is coming out of the memory module, and we're raising the write enable line. The default for the address to write into, that is the number of the register to be updated, is just fine. It is the register destination field from the instruction. So on the next clock pulse, we will write into some register as selected by the register destination field the immediate value. At the same time, we'll be incrementing the program counter and going back to the fetch state. So the next instruction will be coming out of the memory unit. So now let's take a look at that next instruction, and let's suppose it's an ALU instruction, such as the add instruction. So the finite state machine is in the fetch state, and the program counter has been incremented. So what do we need to do? When it's an add instruction, we need to update the registers with the product of the ALU. So we'll be sending some signals to the ALU and to the register unit. So not showing all of those signals here, but basically I'm saying that those signals will be valid in this state. So let's take a look at the code. We'll go back up to the fetch state for the ALU instruction, and that is right here. We are sending the output from the ALU to the register module, and we are raising the enable line to write into one of the registers, and we are supplying a register number, and the register number of A is 0, so we'll be updating register 0, and we also want to update the condition code registers. So we're not needing an extra cycle for this instruction, so the default of going back into the fetch state is just fine. And so after this instruction, we will go into the next cycle, into a fetch cycle, and fetch the next instruction. We will also be updating the register on the rising edge here. So now let's take a look at this instruction and imagine that it's a move instruction. So what do we need to do for a move instruction? Well, we're moving a value from one register to another register, so we need to set the signals to the register module, and so those will be valid here. The register move instruction only takes a single cycle, so we will not be going into any other state. So in the fetch state, when we have a register move instruction, we will be sending whatever is coming out of the register module, back into the register module. Remember that the read of registers from the register module is combinational, so we're by default supplying the source register field from the opcode of the register move instruction to the register unit, and that will cause the value of some register to be coming out on that same cycle. And then on the rising edge, we will be writing to the some register, and we're supplying both the data in as what's coming out of the register in the previous cycle, and we're also using the default of what goes into the register unit. So if I go back up here, we see that the default for the read address is the source field from the instruction, and the default for the write address is the destination field from the instruction. And so if we look at that, then we can see that we update that register and we stay in the fetch state and we increment the program counter, and then we're on to the next instruction. Now let's take a look at the compare instruction. We've got a bunch of instructions to go through, and for every instruction I'll be showing a timing diagram like this. Every instruction always begins in the fetch state, and we've got the instruction's 8-bit opcode coming out of the memory in the same cycle, so the address being fed into the memory previously must have been the address of the opcode itself, and I'll show that symbolically with the letter N. Also, we will have loaded the program counter with the address of the byte following the opcode. So this is the setup for every instruction. The compare instruction will only require one cycle, so we'll be following this fetch cycle with another fetch, and we will be incrementing the program counter and supplying the n+1 value into the memory to fetch the next instruction. The compare instruction computes A minus B using the ALU and uses the condition codes that are coming out of the ALU to set the condition flags. And so during this cycle, we will be raising the condition write enable line, and we will supply the function code for subtract to the ALU. And so on the rising edge of the next cycle, we'll be storing the condition codes into the condition code registers. Now let's take a look at how that looks in the code. So here we are back in the core module, and we have this case statement that looks at the current state of the finite state machine. When we're in the fetch state, we look at the type or the category of the instruction that's currently being executed. And for a compare instruction, we do these two things. The compare will be subtracting A minus B, so we send to the ALU for its function code the 4-bit code for the subtract operation. The other thing we do is we raise the condition write enable line, which will cause the condition codes to be saved. We are ignoring the result of A minus B, so in the ALU operation we were writing to one of the registers, but that defaults to 0, so we don't do that for the compare instruction. For the other aspects of the compare instruction, the defaults will be just fine. So we can see that by default we go back into the fetch state and we increment the program counter. We also see that we are providing the program counter as the input address for the memory unit in order to read the next instruction. By the way, I have eliminated a bunch of material, and earlier in this video I forgot to talk about the default value for the condition write enable line, which is 0. So now let's take a look at the load stack pointer instruction. This instruction will load the stack pointer register with a 16-bit immediate value that's part of the instruction. So this instruction is actually 3 bytes long. The 8-bit opcode is followed by the most significant byte, which is followed by the least significant byte of the immediate value. And so we're going to need 3 cycles to read each of these 3 bytes from memory. Our state machine will go through the fetch state, followed by the execute state, followed by execute 2. and we'll be incrementing the program counter because these 3 bytes are sequential in memory. The instruction itself is located at address n, and the immediate value is at n plus 1 and n plus 2, and then at n plus 3 is the next instruction. So in the fetch state of this particular instruction, we don't really need to do anything special. We're just going to be loading from memory as we would normally, and then on the subsequent cycle we will be loading that most significant byte into the MSB register. So in this state right here, we need to set up the enable line for the MSB register. And then on the following cycle, we'll be fetching from memory the least significant byte, and that will be valid at this point. And so on the following clock cycle, we'll need to load the stack pointer. And what do we load it with? Well, we take the most significant byte from the MSB register and the least significant byte from the memory itself and combine those to get our 16-bit value that will be loaded into the SP register. So for this cycle right here, we'll need to have the stack pointer write enable line valid. So now let's see how that looks in the code. So when we're in the fetch state and we have a load stack pointer instruction, we don't need to do anything special. The default values will work, except we need to send the finite state machine into the execute state, so we need to override the default value of next state. When we're in the execute state and we have the load stack pointer instruction, we need to update the MSB register, so we need to raise this MSB write enable line here. And what shall we write into the MSB register? Well, we write the 8 bits that are coming out of the memory unit. We also need to send the finite state machine into the exec2 state, so we override next state again. And finally, when we're in the exec2 state, we need to update the stack pointer itself. So we will raise the stack pointer write enable line, and the value that we will use to write into this stack pointer is a 16-bit value that is composed of the MSB register for the higher order byte and the 8 bits that are coming out of the memory unit for the low byte. So we'll write that 16-bit value into the stack pointer. Now let's take a look at the add 16 instruction. Its timing diagram is virtually identical to the load stack pointer diagram. The only difference is down here. We're not loading the stack pointer register, but instead we're loading either the XY or the M register. So remember that the add 16 instruction is going to compute a value. It's got a 16-bit immediate value, and that's going to be added to something, and then it's going to be loading one of the 2 registers. So our instruction decoder will take the add 16 instruction, and it will determine which register is going to be loaded with this add 16 destination register bit. It's just 1 bit to determine whether it's the XY or the M register. And we've also got the source register. We're going to be adding this 16-bit immediate value to either the XY register, the M register, or the A register, or to 0. And so we have 4 possibilities. That's encoded with 2 bits. And then the register unit has a 16-bit data input. And we have 2 enable lines, one to load the XY register pair and the other to load the M register pair. And we are also getting out the M register and the XY register combinationally. So we'll be using these to compute a value that will then be loading in using the data input. So just as with the load stack pointer instruction, we'll be reading bytes sequentially from memory. First, we'll read the most significant byte of the immediate value, and we'll be storing it in the MSB register. And then in this cycle right here, we'll have the MSB register with the least significant byte coming out of the memory to build the 16-bit value that we can use to compute what should be loaded into the register on the following cycle. For the first two cycles, both the add 16 and the load stack pointer instructions are the same. So for the fetch state, we can see that the code for the load stack pointer and add 16 instructions is the same. The defaults will work, and all we're doing is sending the finite state machine into the execute state. In the execute state, we again see that the code is the same. Basically, what we're doing is just writing the value that's coming out of the memory to the MSB register. However, it differs in the exec2 state. So here we are updating either the XY register or the M register. So we're raising either the write enable for the XY or the write enable for the M register. And we do that depending on the 1-bit value that's coming out of the instruction decoder that tells us what our destination register is. And so what are we providing as the 16-bit input to the register unit to be written into one of these two registers? Well, I haven't yet talked about this add 16 result, but that's a combinationally computed signal that's set up here. And so let's take a look at that. Here's where it's being set. But first what we're doing is we are figuring out what we're going to be adding. Here is the 16-bit immediate value, right? It's the most significant byte from the MSB register, and the data that's coming out of the memory unit that is combined to form the 16-bit value that will be added to something. But what's it added to? Well, we take a look at the 2-bit field that's coming out of the instruction that determines the source, and that can either be the previous value of the XY register or the M register, or it can be 0, or it can be a 16-bit value that's made from the current value of the A register, 0 extended to be 16 bits in total. So one of those is selected as the starting value to use, and then we add in the immediate value, and that is our value that will be written into either the XY or the M register on the rising edge of the clock on the next cycle. Okay, that concludes our discussion of the compare, the load stack pointer, and the add 16 instructions. In future videos, I will be describing other instructions. So I will see you in a future video, and thanks for watching.